People have already tried to apply this sensor to certain robots, for instance, and this is a really crude way of doing it, is by actually taking the antenna of a moth, keeping it sort of alive, and then putting it in glass caterpillars, and then having it be sent to an amplifier, and then letting chemicals, the pheromones, hit the antennae, and then it will go to a robot. There's a better picture over here. You can hardly see it, but here is the actual antenna, and then this is the robot, and it will make decisions on what chemicals it comes across to turn a certain way, very much like the male moth. So, but this is actually using the actual antenna of an insect. But can we build these kinds of antennae? Now, the first step has been to use exactly how moths achieve chemoreception, kind of trying to copy that. This is one little sensillum, one little sensory organ which has axons and dendrites, and so the actual nerves that go into one of these sensillum, and there are like millions of these sensilla on a moth's antenna. And there are these holes inside on the outside of these sensilla. So here comes a odorant or a chemical, and it goes in through one of these pores and meets up with one of these proteins. And the proteins are very specific to a certain chemical, and this is where you get that specificity for the same species. And then that combination of the chemical and the protein will then attach to the axon and send the signal down. So this is a chemical message that's converted into an electronic message that's sent to the brain. People have been able to actually build something similar to this, where it's a MEMS cantilever sensing apparatus, where they build these tiny cantilevers. We're talking here, this is only 200 microns. So we're a very, very small scale. If you take one of these cantilevers, look at it from the side, they may functionalize it by covering the surface with a material that attracts a specific chemical or molecule. And then if these molecules all stand on this one cantilever, then it will bend the cantilever, and that bending will send an electric signal to the sensor. So kind of similar to what we saw in the moth in the sensillum. So that's what with this MEMS technology, that's how small they can get. That just by a molecule attaching to this cantilever is enough pressure to change the cantilever's shape, and that sends then that deflection sends a message to the sensor. Okay, another type of reception that insects are really good at is mechanoreception. How can they sense mechanical changes in their environment if they have such a rigid exoskeleton? Well, they are not just covered with chitin with that exoskeleton. They have also lots of hairs or bristles that are sensitive to touch. So if you touch the hair, it will bend and send a mechanoreception signal. The body stretching and stress sends signals to the brain. Most famous example is probably an insect that's a blood feeder. It will stretch and stretch and stretch an abdomen with blood, and then stop because it knows if I suck up any more blood, I will burst. Also position, they know exactly where they are in space. Pressure is an important thing that they use to gain information. Gravity, vibrations, lots of examples. do this all in a very small, on a very small scale. Insects are very, very little, yet they get a lot of information out of it. The, I don't want to say the most famous example, but one that I think is really cool is this, this extreme thermal mechanoreception in jewel beetles. These are beetles that lay their eggs in just burned wood. So in forest where there has just been a forest fire, they love to lay their eggs in those dead trees, and then the babies that hatch from these eggs like to feed on that freshly peeled wood. So what these females need is to find forest fires. And forest fires are not that common. So they are actually able to detect up to probably more than 12 kilometers away a forest fire by having these tiny little sensors under their wing as they're flying. The sensor is exposed, and that's sensitive to infrared, which is which would indicate a fire. And this sensor is just a pit with lots of little sensors inside of it, and they're covered with chitin, that exoskeleton material, and it turns out that infrared will hit it, and that will just be enough to change the shape of the sphere, of this bump, and that will change some of the fluid that's in this sensor, and that will then send a signal to the nerve. So we're talking tiny, tiny scale sensors being sensitive to infrared that can be coming from more than 12 kilometers away. So workers in Germany and at UC Berkeley have been working on building an infrared sensor that is based on that what the jewel beetle shows. And it's just a tiny little sensor with a plate, a little, I think it's just 20 microns, a 20 millimeter disc that absorbs infrared light, and then it expands, and this piezoelectric sensor transducer can then measure this deflection due to the infrared hitting it, and then that transmits it into a electric signal. And now, rather than using this type of a special type of a plastic disc, they're actually trying to come up with a disc that is made out of chitin or chitosan, which is very similar. This is the structure for chitin. This is chitosan, which is fairly easy to make by humans, and using that presumably because that will be even more sensitive. So direct inspiration to be able to sense infrared. This reminds me, I think insect cuticle itself is very a great inspiration. It is relatively strong, so the outside of an insect is relatively strong. It prevents water loss, and it is the perfect biomimetic material because a lot of it is recycled. This is just a cross-section of the cuticle. There's an epidermis, just how we have skin, and then there's that cuticle, and then there's an even hardened part of the cuticle. There's a lot of cross-linking between proteins. But all this stuff, this light yellow stuff, is actually recycled as the insect moves to the next stage. It actually it reabsorbs a lot of the cuticle. However, I have not been able to find yet a direct application that uses the cuticle as inspiration, even though it's, I think, the perfect biomimetic material.